Living in a country that has been almost completely swallowed by desert means challenging nature every single day. More than 95% of the territory is covered with sands and stony plains. Rain here is a rarity, and in some regions it is practically absent altogether. Nevertheless, it is precisely here that something happened that just a few decades ago seemed impossible. Saudi Arabia managed to create a gigantic steel water delivery system stretching from the Red Sea deep into the country and sustaining the life of an entire nation. Every day, billions of liters of seawater are taken from the sea, sent to enormous desalination complexes, and then, under high pressure, pumped across the desert through a pipeline network stretching for thousands of kilometers. Delivering water from the coast deep into an arid country is already, in itself, an outstanding engineering achievement. But the real technological breakthrough is turning salty seawater into fresh water, suitable for drinking, agriculture, and industry. It is precisely this that brought Saudi Arabia the respect of engineers all over the world. So how is this invisible steel river arranged? How was it built, and how does it work every day? Today, more than 37 million people live in Saudi Arabia. Practically the entire population practices Islam. But there is one important feature. Most people are concentrated along the coast of the Red Sea and the Persian Gulf. The interior regions of the country still remain an almost uninhabited desert. Saudi Arabia possesses what the whole world dreams of: oil. Under its soil, there are more than 40 trillion liters of black gold, but nature rarely gives everything at once. With colossal oil reserves, the country is forced to spend billions of dollars on producing every drop of fresh water. The average annual amount of precipitation does not exceed 100 millimeters, and in summer the temperature regularly rises above 45 degrees Celsius. To survive in such conditions, Saudi Arabia was forced to create a national water supply system with no analogues. At the core of this system are mainline pipelines laid through the desert. Pipes made of high-strength carbon steel are used, the same kind that is used in the oil and gas industry. The average cost of constructing 1 kilometer of pipeline is about $3 million. And that is without taking into account pumping stations and high-tech desalination plants, each of which can cost tens of millions of dollars. But a logical question arises. Where does the water for this entire system come from? The answer is an almost inexhaustible source: the sea. Seawater surrounds the country, but it is unsuitable either for drinking or for irrigation. On average, it contains about 3.5% salt, too much for the human body and for agriculture. That is exactly why desalination technology was developed. It gave Saudi Arabia almost unlimited access to water suitable for use. The pipelines take water from gigantic desalination complexes located along the Red Sea coast. Each such plant is capable, every day, of transforming up to 7 million liters of seawater into drinking water. The price of this process is enormous energy consumption. The first stage of building an interstate water pipeline is the production of the pipes themselves. They are made from high-strength carbon steel, similar to that used in oil trunk lines. Such steel must withstand constant pumping pressure, mechanical loads during underground installation, and the extreme temperature swings of the desert. Rectangular steel sheets are cut to precisely calculated dimensions. These dimensions make it possible to roll the metal into a pipe with a diameter of about 1.8 meters and a wall thickness of about 25 millimeters. Then, the blanks go into a multi-axis rolling machine. Rollers gradually, step by step, bend the steel until the edges of the sheet come together. Thus, a pipe blank is formed, ready for the next stage: longitudinal welding. After the welding is completed, the pipe passes through a line of straight-through water cooling. This is necessary to reduce the temperature of the weld seam and stabilize the metal. Next, the steel pipes are carefully ground along all edges and corners. This makes it possible to remove burrs and achieve perfect geometry before further operations. Then, both ends of each pipe are processed with bevels for welding. In this way, optimal contact surfaces for butt joints are created. Usually, the length of one section is about 12 meters. This is enough to reduce the total number of weld seams and at the same time maintain ease of transportation. Such a design ensures quick connection, tightness under pressure, and long-term structural stability when laying the pipeline across rugged terrain. Finished pipes are moved to open storage yards. There they are stacked in batches and supplied with clear marking for logistics accounting. Then the sections are lifted using cranes or forklifts and placed on specialized transport platforms. The pipes are securely fixed to avoid deformation during transportation. After that, they are delivered hundreds of kilometers to the construction site, where they will be welded directly along the route of the future pipeline. Pipeline installation begins at large assembly bases located along the future route. Here, fully fabricated steel sections are grouped by diameter, length, and installation sequence. Engineering teams conduct a final visual inspection. They check the straightness of the pipes, the condition of the protective coating, and the identification marking. Proper organization at this stage is of decisive importance. It allows maintaining a continuous work process, avoiding delays, and minimizing mistakes in the harsh desert environment. In parallel with preparing the pipes, surveying groups begin work in the field. Using GPS systems, electronic total stations, and terrain data, the exact pipeline line is determined. The future route is marked directly on the ground surface with stakes and clearly visible markings. This stage is critically important. The pipeline must follow the most stable and safe path, avoiding weak soils, zones of shifting sands, and areas subject to erosion. With the route length measured in hundreds of kilometers, the accuracy of the route directly affects the durability and reliability of the entire system. Before starting to dig the trench, the construction site must be cleared and leveled. This is needed so that heavy equipment can work without interruptions. Along the route, temporary technological roads are laid. Trucks, excavators, welding crews, and transport with materials move along them. Site preparation also includes measures to suppress dust and stabilize sand. This ensures normal visibility and personnel safety. It is precisely this stage that lays the foundation for uninterrupted work at all subsequent stages of construction. After the route is approved, heavy machinery comes into play. Tracked excavators begin digging the trench strictly along the marked line. The width and depth of the trench are maintained with high precision to ensure correct pipe laying and subsequent backfilling. The excavated soil is sorted right on site. Suitable material is left for backfilling, unsuitable material is removed. Maintaining uniform depth and accurate trench geometry is necessary in order to avoid pipe deformation or displacement after installation. However, not the entire route runs across a flat desert. In certain sections, the pipeline crosses steep and rocky mountainous areas. In such places, mechanical excavation becomes impossible. Then, blasting operations are used. Engineers place controlled charges directly in the rock and detonate them step by step. The blasts crush the bedrock strictly along the specified line, forming a trench of the required depth and width. This method makes it possible to continue construction even in extreme landscapes, while the pipeline remains buried, protected, and stable. After the earthworks are completed, the pipes are not laid directly on the bottom of the trench. First, a special bedding layer is formed. As a rule, fine sand or screen soil is used. This layer evenly distributes the load and reduces local stresses on the pipe walls. The base is leveled and slightly compacted to reach the required elevation. In desert conditions, where soils are dry and loose, this stage is especially important for the long-term stability of the pipeline. To lay large diameter pipes, a construction corridor about 40 meters wide is prepared in advance. This allows all installation stages to proceed continuously. On average, the construction pace is about 1.5 kilometers of pipeline per day. Pipe sections about 18 meters long are chosen in order to reduce the number of field weld seams. However, such dimensions impose very high requirements on lifting, transportation, and alignment precision at every stage of installation. At the welding site, a hydraulic internal line-up clamp is installed inside the pipe. It expands around the entire perimeter, rigidly fixing two pipe sections in an ideal coaxial position. This makes it possible to maintain precise alignment up to and during the execution of the root weld pass. The welding process is largely automated. About 80 specialists and dozens of highly specialized machines are involved in the work. Such a system is capable of performing up to 150 welded joints per day on pipes with a diameter of 42 inches. After welding is completed, each joint undergoes automated ultrasonic inspection. This makes it possible to detect any internal defects even before the pipe is placed in the trench. Then the joint insulation crew cleans the surface with abrasive treatment. After that, a multi-component liquid epoxy coating is applied. It forms a strong, completely hermetic protective layer that shields the metal from corrosion and damage. Before backfilling, the assembled string of pipe is lowered into the trench. For this, side boom pipe layers are used, specialized track machines for installing large diameter pipes. Several such machines work synchronously along the route. Each of them lifts a section of pipe using soft slings and steel cables without damaging the protective coating. The pipeline is raised evenly and kept in the air while the machinery slowly moves along the trench. Here, ideal coordination is required. Any twisting, bending, or contact with the trench walls is unacceptable. When the position is verified, the pipe is lowered gradually, centimeter by centimeter, until it lies exactly in the center of the trench on the prepared base. Throughout the process, surveyors monitor elevation marks, straightness, and the natural curvature of the pipe to eliminate internal stresses. This method ensures fast, controlled, and exceptionally precise laying, ideally suited for extended desert routes. After the pipe is laid, the trench is backfilled in several stages. First, a fine protective material is used to protect the pipe coating. Then the previously excavated soil is returned. Each layer is mechanically compacted to the specified density. This reduces the risk of subsequent settlement. In desert conditions where the soil structure is affected by wind and extreme temperatures, high-quality compaction is of decisive importance for the service life of the pipeline. The entire system begins far beyond the land, in the open sea. The process starts with direct intake of seawater, which through special channels is directed deep into the country, ensuring a constant and uninterrupted flow of raw water for the desalination complexes. Large intake lines are first placed in the coastal zone. Installation crews carefully verify the position of each section before lowering it into place. For this, heavy lifting cranes mounted on barges or coastal platforms are used. As the pipes advance toward the shoreline, individual segments are sequentially connected, forming a single main line. It is Rashitana for constant hydraulic load and continuous operation. At this stage, accuracy is of decisive importance. Even a minor deviation can affect the durability of the system and the efficiency of flow in the future. After assembly is completed, the intake line is reinforced with bearing frames and securely fixed on the seabed. Seawater flows through the pipes to the inlet filters of the desalination plant. Intake is carried out at a distance of several hundred meters from the shore. Protective barriers and grates are installed here, which zadерживate large floating debris and prevent marine organisms from entering the system. A pipe with a diameter of 63 centimeters is capable of drawing up to 15 million liters of water per day. This is more than 10,000 liters per minute already at the inlet. Powerful pumps push the water to the main technologiczki blocks. Along with the water, uninvited inhabitants of the sea sometimes enter the system. Jellyfish, crabs, and even small fish can end up in the path of the flow. To completely prevent their proniknoveni, a large-scale filtering grate is installed. It retains everything that exceeds 4.5 millimeters in diameter. After that, the water passes through finer filters that remove the remaining large particles. Even after the primary screening, the water remains saturated with suspended particles. The solution is filtration. This stage takes place in special tanks. Under the action of gravity, the water slowly passes downward through layers of sand. The gaps between the grains of sand are so small that only water passes through them. All twirly particles are trapped inside the filter. The sand, at the same time, constantly moves downward against the water flow. Contaminants settle on its surface and are removed from the system. After this stage, the water looks significantly cleaner, but it still contains millions of microscopic particles. Everything larger than approximately 1/10 of the thickness of a human hair is removed. The next stage includes active mixing of the water. Large blades create uniform movement inside the tanks. At the same time, 2 chemical reagents are added to the water. The first is sodium hypochlorite, used as a disinfectant. The second is gelazo chloride, a coagulant. It forces the tiniest particles of sand and contaminants to stick together into larger flakes. These formations become heavier and gradually settle to the bottom of the tank. At this stage, most of the contaminants are removed. However, the water is still not clean enough for the key process, desalination. After fine predvaritally cleaning, the water enters a cartridge filter system. This is the last defensive barrier before reverse osmosis. Inside each housing, there are several filtering cartridges. They are made of tightly compressed fibrous layers with pores sized from 1 to 5 microns. Water moves from the outside inward through the cartridge. Microscopic particles get stuck between the layers of fibers. Purified water passes through the walls and moves on. When a cartridge reaches its contamination limit, engineers promptly remove and replace it. This allows the system to work continuously with maximum efficiency. However, this miracle has its price. Producing 1 cubic meter of such water costs approximately $5. For comparison, in the United States, the same unit of water can cost only a few tens of cents. This clearly shows how expensive life is in conditions of extreme drought. Now you know how one of the largest water systems on the planet works. From taking water in the open sea to supplying it to homes and cities, every stage is built with engineering precision. This is not just pipelines and plants. This is an invisible river of steel sustaining life where nature almost left no chances. This is what the full path of water looks like in Saudi Arabia, from the salty sea to a glass on the kitchen table. See you in the next videos.